the last episode we introduced you to 40H, which is a different take on the Ford language. If you haven't seen it yet, I advise you to take a look at that one first. It will make it much easier to understand what I'm talking about. So, without further ado, let's dive right in. You might wonder how loops and conditional are resolved. Well, sorry to disappoint you, but it's much like how ordinary for does it. Let's take this simple begin while repeat loop. If the condition of the second line isn't met, the while on the third line will terminate the loop. The repeat on the fifth line will make a jump back to the begin on the first line. Nothing fancy here. In order to resolve all jumps, we need an extra stack, called the control stack. An entry on the control stack consists of two parts, a reference and an address. The reference refers to the kind of conditional or loop we encountered. And we'll see why that is important later. Note, nowadays some compilers refrain from storing a reference, but personally I don't think that's a good idea. Another thing, the control stack has a fixed size and only exists, at least in 40H, while you're compiling. If the compiler complains you're nesting too deep, that means you're really doing something wrong. Remember, Ford can only thrive when you're creating small words. If you exceed the limits of the control stack, you are not following that paradigm, I assure you. So let's start compiling. The -2 is a number, so we can push that one on the stack. Then we encounter begin. It may surprise you, but begin doesn't compile to anything. It just pushes its reference and address on the control stack, and we're done. DUP is a built-in, so we compile that one straight away. The same goes for 0 less. Note that none of these require an operand. Then we get to while. While is what we call a conditional jump. It only jumps when the top of the stack holds 0, like if. Of course, at this moment we don't know where to jump to, so we leave that be. It also pushes its reference and address to the control stack. The +1 is a built-in, so no problems here. Then we encounter repeat. That's where the real fun starts. First it compiles an unconditional jump, although it doesn't know where to jump yet. Then it takes the top of the control stack. It expects 0 or more whiles, which are resolved first. For that it determines what the next address is, which is 06. Then it uses that address to resolve the jump at the address it retrieved from the control stack. Done. After resolving all while references, it expects a single begin reference. And now you see why these references are so important. If we had an unresolved if reference lingering on the control stack, an error message would be issued, which wouldn't be done without that reference. The address would have to be considered at face value, and that may not be correct. Anyway, this entry had a begin reference, so it's valid. Its address is used as a target for the jump we compiled earlier, but notice the difference. The address of the while reference was used to locate the jump instruction that had to be patched, while the address at the begin reference was used as a target for the jump instruction. Now, we introduced several segments to you last time, so it's time to cover the final one, the string segment. This is where all string constants are stored, which are used by .quote and squote, for example. Every 40H source is loaded entirely into memory, like Turbo Pascal. And that's where we start. Take this little program. The red arrow is our cursor. It keeps track of what we have parsed. So first it parses the .quote, and that one in turn parses everything until the next quote. But there's another pointer, a blue one. It starts off at the beginning of the source just like our cursor. It compiles .quote with its current address, then the string constant is moved to the beginning, and finally the pointer is increased. The next squote is parsed and compiled with the current address of the pointer. The string constant is moved just after the previous one, and the pointer is increased again. count is parsed and compiled, type is parsed and compiled, and finally CR is parsed and compiled. But our pointer is unchanged. The last.quote, however, is compiled again with the current address of the pointer, then the string constant is moved, just like we've seen before, and the pointer is updated. We're done. Whatever remains of the program is turned into the string segment. Its actual size can be calculated by the current size of the pointer, so we just have to shrink the segment accordingly. Now we've seen all the different segments. How does it fit all together? From a C perspective, the compiler returns a pointer to a structure called hcode. Actually, it's just the top of the iceberg, since there's a lot going on here. The header contains not just the sizes of all segments, but also the pointers to all those segments. It also holds the execution pointer, which points to the actual instruction which is executed, and the last error which occurred. Note that when 40H throws an error, there's really something fishy going on. An error, any error, holds execution immediately. That construction makes it very easy to pinpoint which instruction caused the error, since the execution pointer is frozen in time as well. When compiling, the string and code segments are created, and those are the only segments which are returned after compilation. Of course, the symbol table is also created at compile time, but it's usually discarded, unless you explicitly want to do a symbolic decompile. In that case, it can be retained, but only if you ask nicely. The character and integer segments are only created at runtime and are sized according to the information in the header. When execution is done, they are discarded, unless execution is halted in a very specific way. Then execution can be resumed from the exact point where it was halted, with all information intact apart from any open files, that is. But what's the deal with all those different segments? Well, we're all familiar with the von Neumann architecture, where we have just one big blob of memory that can either be used for code or data. All addresses refer to that very same memory space. But things can be different. There is such a thing as a Harvard architecture. Here we have two different blobs of memory, one for code and one for the data. A data address is different from a code address, since the Unistay address may also be very different. It's not all just bytes and words. The same goes for 40H. All segments are addressing different units. But how does 40H know which segment it needs to address? Quite simple. cfetch gets a character, and you'll find that one the character segment. Fetch gets an integer, and that one can be found in the integer segment. And finally, fetch C may be unfamiliar to you, but it's actually part of a word set that is supported by various Word vendors. But it was never officially adopted by the ANSWORD standard. It was especially created to access the code segment of a Harvard architecture, and in 40H that's what it does. The string segment is a no-go area. It's only accessed by Ford itself, like when you're executing .quote. All these segments have their own address space. For instance, you can't feed an address in the internet segment to cfetch, but it will still only access the character segment. And yes, it also means you can't mix integers and characters in the same segment. Well, okay, you can, but let's say it requires a little trickery. Anyway, I'm Hans Bezemer, and this was another episode of Back and Forth.